Good morning, afternoon, evening, everyone. Thank you so much to our Google partners for organizing the workshop where we can present and discuss our interim results with the colleagues and collaborators. My name is Nataliya Tkachenko. I am a research associate at the School of Geography at the University of Oxford, and I would like to talk today about the project we have been conducting in collaboration with Panthera over the last 6 months. The project entitled Conservation Cartography Meets AI, How Can We Save Big Cats with Maps? So apart from myself, our team benefits from the wonderful expertise of the colleagues from Montana University, Kevin McManigal and Dr. Hugh Robinson. Hugh is also a director of applied science at Panthera. We are also enormously grateful to Google AI4SG Good team for their continuous support in both in terms of technical provisioning and expert advice. So just to introduce some brief context to our problem, along the well-known and alarming biodiversity crisis we are facing, the particular hit was taken by one of the most charismatic species, wild cats. So not only their populations decreased at unprecedented levels due to various factors. For example, we lost almost all the tigers, 90% of cheetahs and lions, and where snow leopards are also on the brink of extinction. So if not reversed, we are going to face an unprecedented ecological collapse, as not only we will lose one of the most charming and charismatic animals, but also one of the most significant apex predators, which regulate all the subsequent food chains in the animal and plant kingdoms. So various international conservation organizations and governments are making active efforts to protect the declining and endangered species by designating parks and protected areas. According to protectedplanet.net, there are currently around 200,000 terrestrial designations alone, which are supposed to protect and reverse the decline of various species. However, according to various reports and news media, their success is mixed and greatly dependent on the social, economic, and legal situations in those regions. Conservation organizations, including Panthera, concluded that less than 50% of those designations contain enough information or information at the required level of granularity for management. Hence, protected areas are largely regarded as paper maps, lacking necessary informativity to be fully functional and operationalized. So to dig deeper into this problem of paper maps, AI4SG Good enabled us to team up with Panthera to look into the dearth of information problem. As a case study, we picked the Niakola-Koba National Park in Senegal, which is a famous biodiversity hotspot situated on the banks of the Gambia River. Its wildlife includes elephants, lions, leopards, chimps, baboons, hippos, and numerous bird species. It is also one of the world's heritage sites, covered with large patches of wooded and seasonal wetlands, which can make its mapping also an interesting and useful challenge. So, Panthera as a conservation organization have been using maps as the main weapons against poachers and declining animals populations. Specifically paper maps, the topological standard 1 to 25,000 scale products have been produced and printed out to be used in fields. So, the ongoing work has been performed in Nepal, India, Senegal, and Malaysia, where total areas of each park has been broken into quadrant fragments, which around 13.4 kilometers on each side. So in total, it has been so far been produced around 69 map sheets, and this work has been completed in under 208 weeks. It took almost 4 years for the team to complete this work. So just to put in the context, mathematical problem is that it takes around 3 weeks per map sheet to be produced, which is awfully long time for a map to be produced. And going into further details, for example, Tigers Forever Sites Alone, which is one of the programs which is conducted within Panthera organization, it requires around 315 map sheets, which means that it will need around 18 years to be produced. So for conservation organizations and for biodiversity crisis we're facing, it's a very, very long time, so we need to act much faster and more efficiently. So here I would like to show you the examples of the maps which have been already produced for near Kolkoba Park in Senegal. So you can see here on the map on the left that 20 map sheets have already been generated manually, and on the right is one of the examples of such topological products. So it shows that the granularity of the information required is quite high, and therefore precision is also very important, because this information then further used by rangers in fields and also for mapping various migrating populations of animals. So to answer the question, what is the purpose of these maps? So first of all, the aid field navigation of anti-poaching patrols in quite fragmented field settings. They also should facilitate data collection on the poaching activities and all kinds of criminal activities within and across various parks. And also help rangers collect data on animal populations for ecologists and scientists from various camera traps and field signs. So the question and one of these challenges which has been posed and presented for AI for social good teams was, how can we meet these goals faster and especially cheaper as well? Because manual digitization is currently absorbs the bulk of the efforts, of the budgets and work to be able to produce these maps, let alone that it takes awful amount of time, which we don't really simply have to save the species. So we teamed up here as specialists in remote sensing, in artificial intelligence and digital mapping, in order to be able to brainstorm, first of all, how we can approach this problem and speed up the whole process of mapping conservation areas at a higher level of granularity and faster. So from Panthera, we have received already created training data for near Kolo Park, which is result of the 20 map fragments, which I already presented on the previous slides. And these maps, when combined together, they represent a training segment, which is around 1/4 of the entire area which need to be mapped. So these training segments consist of 11 categories of objects we would like to discover and map. So, but they also fall into 3 main categories. They are buildings, different huts, and various administrative designations. They also water features, which can be rivers or smaller streams, and also seasonal wetlands, which I already mentioned before, and also various roads and trails, which can be of various degrees of importance, from ranging from primary routes to the most difficult to trace and discover paths. So first of all, the exploratory part of our work included development of 2 very simple statistical classifiers, which are support vector machine and random forest. As data sets, we used 2 types of free multispectral data sources, such as Landsat 7 and 8 and Sentinel-2. And also we decided that we're going to balance our training across 18,000 points, therefore 6 points per each class of buildings, class of water features, and class of roads and trails. So our preliminary results demonstrated that the highest accuracy was achieved with help of, rather unsurprisingly, with random forest classifier across all the imagery inputs, and this accuracy was around 87%. So the highest accuracy was achieved so far, and 91% received for polygonized water features, and the lowest for the narrow linear features such as roads and paths. Small buildings and huts have received accuracy of around 77%, which was rather unsurprising given the quite coarse resolution of Sentinel and Landsat imagery. So, nevertheless, despite this initial kind of experiences, we can say that free data allowed us to extract around 60% of all the desired topographic features. So, there is still opportunities for improvement, of course, but we still can get the data and speed up the process quite efficiently, significantly. So, over the next steps, we are planning to do the following. We would like, first of all, to granularize our classes training and extraction, and rather than looking into 3 domain classes, we're going to break them down into independent features. So we also would like to test these models on higher resolution data, specifically for Planet Labs or McSharry imagery, the ones which you will be able to get access to. We would like to develop a kind of more advanced deep learning assisted segmentation and object detection algorithms in order to achieve the highest and much closer to 100 accuracy of the topological granularization. There also has been discussions about possibility of testing generative adversarial networks, which will help us to, for example, translate information directly from park to park, and rather than concentrating on object-to-object translation, we can translate directly from park to park or from map to map. And of course, we would like to see if we have time and resources, we would like to scale out our results globally and to publish them on Google Earth Engine if we will have a possibility to do so. Thank you very much, and we are open to your questions.
A very good evening to all, and it has been a pleasure to be associated with the Google AI for Social Good Initiative 2021. I am Navneet Goyal, and I'm joined by Poonam Goyal and Anushri Karve. Myself and Poonam are from Department of Computer Science, BITS Pilani campus, and Anushri is from WCS, the NGO associated with us for this project. And the title of our project is Collating and Analyzing Multimodal and Multilingual Data for Countering Wildlife Crime. And let me just quickly introduce you to the team. From BIT side, we have Poonam, myself, Shekhar, who's an ME student, Anish and Sunil are PhD students. And from WCS side, we have Anushri, Aristo, Shama, and Nikita. And Google Connect for this project is Garima. So the problem that we identified was based on these observations, and I'll just quickly go through these points. So India contributes about 8% of global wildlife, despite having just 2.4% of the total land area of the world. But despite this, it is home to 45,000 plant species and 91,000 animal species. And there's a huge global demand for India's flora and fauna, which is the main cause behind increasing illegal wildlife trade in recent times. And according to WPSI, 287 tigers and 1346 leopards have been killed between 2009 and 2017 in India. So while studying these problems or this data, we realized that there is no centralized wildlife crime repository which can be queried and analyzed by the law enforcement agencies and the NGOs. So based on this, we tried to put forward a project proposal which was about collating this data for the LEAs and the NGOs. So the main objective of our project is to reduce wildlife crime using AI. And for this, we needed to collate multimodal, multilingual data, and that formed the major chunk of our project. Most of the time we have spent so far is on this part. And so as to provide comprehensive data about wildlife crime and related events to all stakeholders. And once we have collated this data, we plan to analyze this data for identifying crime hotspots and trafficking routes, identifying modus operandi, identifying criminal networks. So these are the three main things that we have listed as part of our project. And of course, for collating multimodal and multilingual data, again, we need to use a lot of AI. And of course, for the second part also, we need, for analyzing, we need a lot of AI models to be built. The challenges that we faced are that the data is multimodal and multilingual, so that adds to the complexity. And the other complexity is that the data is spread over different media. It is there on the web, it is there on TV channels, it is there on social media, print media, etc. So we need to look at all the different media to collect information. So collating information about a crime event is basically very typical because there are multiple news reports on the same crime event in same or different languages. And sometimes the information that they provide are contradictory in nature, so we need to be very careful when we collect this information. And by doing this, we are trying to create parallel corpora for different languages. I'll talk about this later in the presentation. And then the other challenge that we faced was that we being a complete story, say a crime event is there, and then there are a lot of follow-up events. And how can one identify these follow-up events for a given event, right? So this is a very, very challenging task as we are seeing it. I mean, we have not started to work on it, but this is one big challenge that we see. And here are some of the things that the marked in red. So we are exploring multimodal learning models for dealing with multimodality. And for multilinguality, we have proposed a concept of language triplets, which again, I'll talk about it later. And for handling different kinds of media, we have creating separate pipelines. And for English language, we have done this already. And for multiple news reports and how to bring them together. So we have introduced this concept of semantic duplicates, and these duplicates can be there in same language or in different languages. And for doing this, we need this concept of noun synonyms. We need to identify noun synonyms, and we need to look at document similarity of named entity heavy and sensitive documents. So we have done quite a few experiments on this, and we have found that the similarity measures, document similarity measures that are there are not very suitable for this kind of job. And we being a complete story, as I mentioned earlier, so we are trying to establish temporal relations between events. And for all this, while working on this data, we decided that we'll use graph databases for storing this data. And of course, once we have stored this, for querying this data also, we'll put everything in graph databases. And these are the kind of challenges we face. So this is one reporting which happened on NDTV news channel. And you can see there is an image, so the multimodality is very evident here. But this image is actually related to the event that they're talking about. But on the other side, this is another reporting on Z News, and this is about seizure of huge consignments of live animals. But the image that is shown here is not related to this. So this image is for representational purposes only. So these are the challenges that we are facing as far as collating information is concerned. And the solution that we have proposed or we are working on is that we first segregate the news articles based on language. So And we are considering 3 languages, basically language English, Hindi, and a regional language. And we'll develop AI models for identifying semantic duplicates, which are in the same language or which are there in different languages. And noun synonyms becomes a very important issue in this. And then once we have identified semantic duplicates, so basically by semantic duplicates, we mean that articles which are reporting this about the same event. And once we have done this with some confidence, we'll be doing feature augmentation using them. And again, in the same language or in cross language, because some features may be present in one language, one report, but may not be there in the other report. So we'll try to bring this. And missing values also can be filled up using these semantic duplicates. And we plan to store them in union find data structure for analysis. And 3 identical databases and a query interface would be developed. 3 identical databases in 3 different languages will be developed. And the work done so far is, as I mentioned earlier, we have collated a lot of data using in English language. And we have also done the modeling part for this, how we are going to model this. So we are going to use object orientation and we'll store the data in graph database. Focus crawling we have done, we have completed this already. And the manual annotation of named entities and their attributes and relations have been done for news articles. And this data we are preparing for automatic tagging. So this manual annotation part is complete. And now we are building AI model for automatic tagging so that we can just take these documents from the web or articles from the web or any other media and then automatically tag them. And data extraction we plan to complete by February 2022, and storing this data in a graph database will also be completed by February 2022. And I'll now point you to some of the research problems that we have identified while working on this project. And they are all related to NLP. And so the first problem is identifying semantic duplicates. So multiple reporting about the same event. So, and as I said, same language, and they can be in different languages. And addressing the above problem, we'll be doing it in 2 different ways, using structured, and one is using unstructured data and the other is using structured data. And the research gap that we have identified is that entity heavy and entity sensitive data. So they are there are lots of named entities in this, and if you change one named entity, the document will change completely. So existing document similarity methods like models like SIM-CSE is unsatisfactory, as I'll show you in the next slide. So these are like 4 cases that we have, 3 cases basically we have discussed. And these are some of the models that are there. So you can see that first column, second column basically, same event, different articles. And they are in A and B, text A and B, some representative text is presented here. And in the third column, we have different events and different articles, so totally unrelated. And third one is same article, and we have changed some named entities in them, just to check. And we can see here, the main observation here is that the similarity scores given by these models are more or less the same in the range of, I think, 0.85 to 0.90. So there is not much change that we see here. So how to address this problem? So that's what we are working on. And the second problem that we are working on is linking related events. So say, for example, if these are 3, suppose this is the first event is the crime event, that is tiger found dead in Ranthambore National Park on 18th October. Tiger claws seized in Jaipur, 24th October, after a week. And 2 poachers with firearms arrested near Ranthambore, 15th November, 2021. So these are related to the same crime event. I mean, the crime event is the first one, and the other two are related events, temporally related events to the crime event. So how do we link them in an automated way? So this is one major problem that we are trying to face. So that once we are able to link them, then we'll be able to understand the modus operandi, the criminal networks, and the trafficking routes. And this information will be very, very useful for the law enforcement agencies. And with that, I'll stop here. And I thank Google and Google AI for Social Good for giving us this opportunity to work on this very interesting and challenging problem. Thank you.
Hello everybody, we are presenting the project exploring and managing human-bee conflict in Asian cities using AI. The team members include Smitha Krishnan from the Alliance of Bioversity International and CIAT, Axel Brockman, Rajat Siddhaganga from National Centre for Biological Sciences, TAFR, located in Bangalore, India, Waigwa, Sylvain Grizin from the University of Tokyo located in Tokyo, Japan and Toulouse, France, Renu Singh from Google Incorporated located in Paris, France. First, we would like to thank Google for the AI for Social Good grant and facilitating the collaboration from different disciplines and helping us identify the right match. Thank you. Now, we would like to start by presenting to you the background of our project, the current progress, and what we eventually want to accomplish. About 87.5% of wild flowering plants globally are animal pollinated, more so in tropical countries such as India. A wide range of crops are pollinator dependent too. In fact, in more than 70% of all the major food crops, fruit set is enhanced by pollinators. Among them, a number of nutritious crops such as nuts, fruits and vegetables are highly or completely pollinator dependent for fruit set. Examples: cashews, almonds, melons, cucurbits, apples, etc. Also cocoa too. In India, pollination services are mainly provided by wild bees, among which, wild honeybees. There are 5 native bee species and the imported western honeybee, Apis mellifera. Only the cavity nesting species, Apis cerana and Apis mellifera, can be used for beekeeping. However, all honeybee species, and in particular, the giant honeybee, Apis dorsata, are important for pollination services. Currently, there are no conservation efforts to protect those wild honeybee species. In fact, they are often treated as pests and indiscriminately eradicated in most cities. Typically, Apis dorsata nest on tall trees in forests, but in the cities, they use tall buildings, e.g. balconies, as nesting sites. People are afraid of these bees because of their size and the capability of these honeybees to fly at night. In the nights, they get attracted towards light in the apartments and enter through open windows. Colonies are generally relatively calm, but when agitated, they launch an attack with hundreds of workers. These honeybees are viewed as nuisance, and people call pest management to eradicate the colonies nesting in such structures. To address this human-animal conflict, we ask the following questions. 1. What is the population size of Apis dorsata colonies in Bangalore? 2. How many colonies get eradicated? 3. Why do they congregate and where do the colonies forage? To estimate the population density, we overlaid 1.5x 1.5 km grids on Bangalore city and randomly picked 10% of the grids and scanned through this area and counted the colonies within the grid. We have already surveyed 50% of the grids. This data will help us extrapolate the density of colonies within Bangalore city. To address the second question, we got in touch with the Bangalore Apartment Federation, which represents about 1,000 apartment complexes all over Bangalore and have their support in our initiative. We plan to organize a webinar where we would present our research question and request them to fill in a questionnaire that would help us estimate how many colonies are eradicated every year. This will help us evaluate what we are losing in terms of pollination services. To address the third question, we plan to use GIS and AI. The land use surrounding the colony aggregations would be evaluated and the foraging dances that the bees perform to communicate the availability of food sources nearby to the other foragers at the nest will be recorded and decoded using AI. Next, we will show you how to decode the waggle dance based on the knowledge from previous researches. A honeybee forager who has found a good resource, example, a high-quality/quantity source of nectar or pollen, returns to the hive and performs a waggle dance, a communication event that recruits nestmate foragers and directs them to the specific resource location. The directional information is encoded in the waggle run, the portion of the dance where the bee waggles her body from side to side for a particular length of time while moving at a particular angle on the vertical comb. How long she waggles in seconds roughly corresponds to how far she flew from the hive in kilometers. Her waggle orientation, clockwise from vertical, corresponds to the angle of the resource relative to the sun. So what a waggle dance looks exactly like. Here is an example. A bee in the center of this video is dancing. Please note, as you can see, she is repeating these waggle runs many times within a dance. The experimenter uses the average waggle run duration and average waggle run direction as means to determine the location of the food source. Moreover, to take such high-resolution videos with clearly visible dancing bee is cumbersome and requires well-controlled light conditions for video acquisition, which can only be generated by housing colonies in indoor observation hive, such as this shows the video record of Apis mellifera. However, our target, Apis dorsata, cannot be kept in an observation hive and we need to record the dance behavior on site. So what does a video dance recording of Apis dorsata look like? Here on left represents daytime and right represents nighttime recording. Can you find out the waggle dance from those videos? Please note there are several dances happening at the same time. Humanly, it is extremely difficult and error-prone, but we expect that AI-based approaches will be able to analyze the dance recordings from videos taken under natural conditions, while substantially reducing errors. So what will be the challenge for our task? First, as you may mention, bees are not just dancing once, they are repeating the dance, which will increase the noise in the dance analysis. So just observing the dances from one hive is not enough, we need to watch as much as possible. Second, even though we are expecting AI-based approaches to help us analyze dance recordings from videos taken under natural conditions, there are no previous AI-based work on Apis dorsata. This means we do not have raw data and annotated data that can be fed into a model. So we need to create the data from scratch. This is a time-consuming, laborious process. Thirdly, once we get enough data, we may want to change the way of problem solving. Instead of seeking the answer from high-accuracy waggle dance decoding using high-quality video, we could accept not that high accuracy but with big enough data that can be used to estimate the visiting histories of bees. In order to record long-duration video at many nesting sites at the same time, we needed a low-cost, flexible and easy-to-mount camera system. So, we designed a camera system using Jetson Nano Developer Kit with Pi Night Vision camera to record video. As you can see in the picture at the right side of the screen, this camera is easy to mount and record video for long duration. And it is configured to record at 720p resolution at 60 frames per second for best video quality. The video captured using this camera can be used for annotating waggle dances and decoding the same. As said previously, videos of hives were collected in Bangalore and its surroundings. There are only a few dances per video, so each video is analyzed by an ecologist with field knowledge about dancing bees to extract timecodes of the beginnings and endings of the dances. Then, raw videos are cut at these timecodes to make little clips of dancings. These clips are annotated, which means that bounding boxes are drawn at each frame of the dances around the corresponding dancing bee with a directional vector, coding the bee orientation, added. This orientation corresponds to the angle between the bee body and the angle of the zenith of the sun. This way, a training test validation set for the deep learning model is created. Today it is made of 147 dances. We tried to apply a UNet deep learning network for segmentation invented for medical images analysis, trained by researchers from Okinawa University on bee tracking. It worked well for clear and non-blurry bees. Now, we aim at making our own network with our own dataset to go beyond this tracking task with the decoding of the waggle dances. Compared to this paper, we also have some unseen constraints to overcome: high-density populations of bees, different bee species, non-controlled light, videos from wild hives. As you can see, everything is still ongoing. Our next plan will include completing the remaining 50% of the field survey for Bangalore City. We are working hard to procure map from the National Remote Sensing Center of India to generate land use land cover maps around Bangalore. At the same time, with the help of Google, we will also try to build a proper model that can detect and track waggle dance, then decode them to arrive at our final goal. Thank you, and we are looking forward to any constructive suggestions and open to questions.
Hello everyone, in this video I will be introducing our latest work on human-in-the-loop chimpanzee identification, which is funded by Google AI for Social Good project. My name is Li Han, coming from the University of Queensland in Australia, and we have in total 6 group members for this work. Tropical forests and the animals within them are disappearing at an alarming rate. As a representative example, West Africa chimpanzees have been classified as critically endangered due to massive population declines in recent decades. Established efforts have aimed at increasing protection for the conservation of chimpanzees. Thus, we study chimpanzee conservation to protect tropical forests within them across Africa. Researchers have been using effective ways to monitor chimpanzees and other species by camera traps. These camera traps are increasingly deployed in tropical forests, which allows to observe more of each individual and record their behaviors and other important information about wildlife. These great opportunities don't come without challenges. The cumulative amount of videos made by these camera traps makes it impossible to watch them. For example, here, Wild Chimpanzee Foundation has generated more than 1 million videos, but they only have 5 members in their group to analyze them. Thus, in our work, we address this bottleneck of watching and identifying chimpanzees. To achieve this, we propose to use human-in-the-loop artificial intelligence method to optimize the human effort by leveraging AI techniques to scale up the process of large amount of recorded videos. Now, let me briefly introduce the state-of-the-art identification process for chimpanzees. The identification is done over Zooniverse and previously on your borrower's website. On this website, citizen scientists watch a 15-second video and raise or participate in a discussion thread about the features of the chimpanzees shown in the video. Here is the videos. If 5 citizen scientists can make a consensus during the discussion, then the chimpanzee is confirmed and will be assigned a unique tag or linked to existing tags in the database. Here is some examples of the tags. If no consensus can be made, experts will decide whether any features that citizen scientists discovered can be overwritten or to join the discussion. Therefore, from this body of discussion forum, we have the following data. Here. Discussion text, which allows us to understand how users make consensus. Tag labels, which are also chimpanzee IDs. This allows to link any discussion to a specific ID, because some initially assigned IDs may be merged once evidence shows that they are in fact the same identity. The role of users, which enables to distinguish experts from citizen scientists. And in each discussion thread, they attach the video for which the discussion is raised. Using this unique collection of complementary data, in this project, we model the difficulty of chimpanzee identification task for different videos. The aim of the project is to build a practical task allocation model that can route the task to different users by task difficulty. Notice here, we can route the task to experts, citizen scientists, or even crowd workers, or some software or AI algorithms. When a new video is captured by camera traps, the model can decide where the video should be directed. The data we have created includes 17,000 videos of 700 chimpanzees, as well as discussion thread where expert and citizen scientists discuss about the feature and identity of the chimpanzees. We also extracted the images from video frames sampled at 1 image per second. This gave us more than 200,000 images. We first integrate with open source libraries from Zamba Cloud, that is here for this part, to build a model detecting whether a captured image contains chimpanzees or not. This would be the first step when a new video comes. For each newly captured video, if none of the extracted images contain a chimpanzee, then this video is discarded. In the second step, we estimate the difficulty of processing each video. For the videos and the extracted images, we have 2 group members working on ID prediction tasks, that is predicting ID given the video or image. Each prediction comes with a confidence score, which is the probability of the predicted ID being the ground truth ID. This confidence score allows to define the difficulty of algorithms identifying a specific chimpanzee. By the confidence score, we also find machine may make high confidence mistakes. For example, here in this table, we compare the predicted IDs versus ground truth IDs. Here is the ground truth, here is the predicted IDs. The model is trained on a small subset. We can see that for the chimpanzee named Christine, that is this one, the prediction of Christine is 0.79, this number. While all other predicted labels for this ID are in low probability, which is good here. But for chimpanzee Cairo, this is the 3rd row here. The prediction of Chanel is 0.84, that is this number. So this means that the machine makes a mistake, but it's not aware of that given its high confidence. This type of observation calls for further investigation, which is also in our future work to mitigate such errors. To estimate how difficult it is for humans to identify chimpanzees, we analyze the discussion thread that we have collected from the discussion forums. Here, we list the features that we use to model their difficulties. For each chimpanzee ID, we extract the number of threads, the number of posts in all threads, max number of posts in a single thread, keywords in all threads and their importance. This is done by RAK model from natural language processing. And the number of expert and non-expert posts, length of posts, max length of a single post, and the number of users involved, number of branches, and max depth of a single branch. At the same time, we also have number of images, number of videos that can be linked to each chimpanzee ID. To generate the label of task difficulty for our experimental evaluation, we design an annotation task shown here. We present the video and ask annotators to watch, and then we ask them to give a score indicating the difficulty of extracting the given chimpanzee features from this video and of matching this chimpanzee to existing ones in the database. Here, that is the question 1 and question 2. We send this task to experts, citizen scientists with different working experience, and crowd workers on crowdsourcing platforms such as Mechanical Turk. 3 different types of annotators. This would allow us to estimate the task difficulty for different annotator populations. Once we finish collecting these task difficulty labels, the next step of our work would be training models for task difficulty estimation and performing experimental evaluation. We also plan to work one step further using the predicted task difficulty for task assignment problems, that is this part. For example, routing easiest tasks to novice citizen scientists or even crowd workers who are more flexible to offer contributions at any time, or routing the potentially difficult task and introducing experts into the task when it is necessary. So, in conclusion, in this project, we address the bottleneck of few people watching a large amount of video to identify chimpanzees. We propose to use human-in-the-loop AI approaches to optimize the human effort to scale up the process of analyzing these videos. Because of the current process of chimpanzee identification is done through discussion on forums, we collect 4 types of data in our work: discussion text, chimpanzee ID, users of different levels of experience, and the attached videos. This data collection enables to model the difficulty of identifying chimpanzees from different videos. We first built a model by using libraries from Zamba Cloud to detect if any chimpanzees presented in the captured camera videos. For those containing chimpanzees, we study the performance of the algorithm prediction for specific IDs. By using prediction confidence, we are able to define the task difficulty from an algorithmic perspective. We also model the task difficulty from a human perspective by using the features extracted from discussion thread. To evaluate our methodology, we design an annotation task to assess the difficulty of recognizing a specific chimpanzee by asking annotators to watch videos. And we target at least 3 types of annotators: experts, citizen scientists, and crowd workers. That's all for my talk. Thanks for watching this video.
Hello, my name is Ashwin Shrinivasan. I'm at BITS Goa, and I will be talking to you about the AI for Social Good project on elephant conservation called the Mara Elephant Project. From this point on, I'll turn off my video and just give you an audio narration. So the main issue with elephant conservation in Africa is that African elephants are under threat for 3 main reasons. One, which we all know about ivory poaching. There are also problems to do with conflict with humans, settlements, and the loss of and fragmentation of their habitat. This project is joined with the Mara Elephant Project in the Mara Serengeti area, which has been going since 2011, tracking elephants with GPS collars. In the project, we want to address 2 issues related to human-elephant conflict. First, the detection of elephant movement behavior, like crop raiding, from real-time GPS data, which is time series data. And the second, detection of anthropogenic landscape features from satellite imagery that are relevant to human-elephant conflict, which would be image data. To address the first problem of tracking elephant behavior, we want to build a human-based labeling system for annotating elephant GPS tracking data, and this will be followed by a model-based detection of behavior from the GPS data. We will implement both the labeling system and the model-based prediction along with some visualization tools for alerting both researchers and wildlife managers to provide real-time insight into elephant behavior. To address the second problem of detecting and using anthropogenic features, we again want to build a human-based labeling system for identifying these features from satellite images. This will be followed again by a model-based detection of these features from the images, and these landscape features, which were detected by the models, will be hosted within the organization's database to be used in conjunction with the movement data. So in both cases, you can see that we are after a human-in-the-loop labeling system, which we intend to attempt using a technique called ripple-down rules. So in the first part of this project, which I will be reporting on today, we are looking at a proof of concept to demonstrate the construction of rule-based models for human-in-the-loop labeling of diverse kinds of data. This involves, obviously, a human-in-the-loop, human understandable feature extractors, and a ripple-down rule engine. Now, ripple-down rules are a semi-automated way to acquire and maintain human knowledge systems. It can be used for the consistent acquisition of knowledge about labels, decisions, actions, and so on, where knowledge is usually in the form of rules. They don't have to be, and they're exceptions, usually stored in a tree-like structure, as shown here. So the top vertex is some generalized rule, which is then perhaps overridden by some further specializations, which may then be overridden again, and so on. The basic idea behind the ripple-down rule system is quite simple. For a new data instance, either the decision of the system is correct or the decision of the system is incorrect. If the system is correct, then there's nothing to be done. If the system is incorrect, then we specialize one or more of the rules if they are overgeneral, and we generalize one or more of the rules if they are overspecific. So a ripple-down rule engine can be used in a human-in-the-loop system, as shown here. The human looks at the data and provides supervision on the kinds of features to be extracted. The human also provides model feedback to the RDR engine in terms of whether it is correct or incorrect, and also whether it is overspecific or overgeneral, perhaps. And the RDR engine then automatically tries to correct the model so that it is consistent with the feedback received and with the data seen so far. For the proof of concept here, we aim to show that the same RDR system can be used to acquire and maintain knowledge about different kinds of data. Here we'll be focusing for obvious reasons on image and time series data. I must also say that our neighbors have helpfully added some music to the background so you can enjoy the remainder of the slides. The proof of concept with image data looks to construct RDR-based human-in-the-loop models for an image classification problem, which contains the images like the ones shown below. These are called Bongard-type problems, where images are classified as either positive or negative, depending on the shapes and the relations between them. There are about 400 images in this data set. The time series data, on the other hand, consists of readings from about 60 sensors with about 10,000 time points. and specific time points in the series are labeled as containing anomalies or malfunctions. This is actually some kind of industrial process. So there are 61 time series channels which look like these. The first step in the image classification problem is to translate images to a textual representation of the kind shown on the right here. Normally, we would expect this to be done automatically. For the proof of concept, this has been done for us. The actual feature extraction, which is done automatically, extracts features from the textual representation by constructing all possible relational features of the kind you see on the right. For example, does it have a circle? Are there circles within circles? Are there circles within triangles? And so on. All possible relations are constructed automatically, and for a particular image, each relational feature will have the value 1 or 0, depending on whether it is true or false. For the time series data, we do not employ an intermediate textual representation and go directly to the values of some statistical features, such as the ones shown on the right over here. Now, you may well ask, how did we decide on these particular statistical features, or how did we think that these were important? We don't know whether these are the important ones. These are ones we start with. The point is that the human-in-the-loop system that we intend to develop will allow us to expand or change the feature representation as and when needed. The time series data are not labeled in any way, and we would like to see if there is any pattern to the anomalies in the data. We attempt to do that using a t-SNE visualization of the time series vectors in 2 dimensions, which is shown here on the right. And this visualization appears to suggest there are 3 kinds of anomalies, which is analogous, remember, to perhaps 3 different kinds of elephant behavior, which we will try to classify using the RDR engine. I've shown you here the rules and the tree structure constructed by the ripple-down rule engine for the image classification problem. Since the problem is a synthetic problem, it's not terribly important what the rules say, but what is perhaps worth noting is that how the rules are to be used. So if, for example, the image has a triangle, then it's predicted positive. If it doesn't, then the branch to the left is taken and is predicted negative. But if it does have a triangle, and it does not have a triangle within a shape, then it's predicted as negative, and so on. This is actually equivalent to kind of specialization and generalization in a way that I won't elaborate here further. I've shown you the tree here for the time series problem, where 0, 1, and 2 are the labels of the clusters identified by the t-SNE visualization. You're probably also wondering where the thresholds for the different variables came from, like 12 and -4 and so on. These are either automatically identified to be consistent with the data or can be entered by the user. If they're entered by the user, then the system checks to make sure that consistency is maintained. You can see that the trees were quite small, and in fact for both the image and the time series data, we achieved 100% accuracy on a test set with just 4 revisions of the model. This graph shows you how test set accuracies change with revisions to the model. Usually adding a revision does make a difference to the test set accuracy, but not always, as you can see. But after 4 revisions, we get to 100% on the image data. And the same sort of thing happens with the time series data. So what can we conclude from this proof of concept? 1, that RDRs can be used as an effective tool for acquiring and maintaining models for a variety of different data types and analysis tasks, and that they can work with a human in the loop who identifies relevant features and provides feedback. But these conclusions only really hold if data-specific feature extractors can be constructed for features that make sense for the human in the loop. So back now to the MARA project. For the second half of the project, we are in the process of building human understandable feature extractors for the MARA time series data of elephant movements. And we'll plan to use these features with the RDR engine we developed in the proof of concept. We are also building visualizations using t-SNE and motion charts, and we hope to report back to you on how well our human-in-the-loop system with the RDR engine did on elephant data. Well, thank you for your time and attention. I would like to acknowledge some people in the institutions, students at BITS Goa, Bioversity and Tirthraj, and also my colleagues Paul Compton, Michael Bain at the University of New South Wales for very interesting discussions, always on ripple-down rules. Of course, this project was funded by the Google AI for Social Good program, and BITS funds my professorship at BITS Goa. So thank you again, and see you next time.
Hello, I'm Cedric from Carnegie Mellon University, and today I'm here with Ryan from Carnegie Mellon University, together with Debajyoti and Arindran from the World Wildlife Fund. And today we're very pleased to share with you NewsPanda, a toolbox for analyzing conservation and infrastructure articles. Now, a really big problem a lot of WWF country offices face is that they spend a lot of time and resources looking through various news articles, trying to identify trends, events, threats, stories related to conservation and infrastructure. Now, you can imagine this is a very long process. From start to finish, you have to scrape articles, you have to read them, extract insights, and so on. And so we thought, what if we could have a tool that can automate this entire process from start to finish? Then this would allow WWF to save so much time and so much resources. And so together, we built NewsPanda. And in this diagram, we see the entire workflow from start to finish. Now, every week, NewsPanda scrapes news articles, analyzes them, and forwards the results to WWF site managers for them to act on. Not only that, NewsPanda also plans to eventually launch a Twitter bot to share these articles and insights to the public for other interested parties. Now, if you look more closely at this diagram, you can see that the boxes in brown represent outputs of the pipeline. These include the relevant filtered articles together with our insights. And in the gray boxes, we see the processes taken. These are the features of our toolbox. And in the next few minutes, we will go through these in greater detail. So first, we'll be talking about the machine learning classifier. Here we see a diagram of the classifier. The classifier model itself is the gray box. But what I'd like to emphasize in this diagram is the iterative cyclical pattern of getting new data and training better models. And you can see this iterative cycle in the diagram, which is really the key to our model. So for the first part of this cycle would be training the model. And this process is actually quite straightforward. Also here we see we input the raw news articles, and then we do some pre-processing using sentiment analysis and topic modeling. Then the core of our model will be the BERT encoder. So using all of these features that we get, we can then make predictions whether or not an article is relevant to conservation or to infrastructure. Next, going to the other step in this cycle I mentioned is the data labeling by the WWF experts. Here, our main question is, how do we select the best articles to label? Now, the idea is that our machine learning model can very quickly label thousands of articles, but this is not true for humans. Humans have limited time and limited resources, And so we really have to select the best articles in order to maximize the expert knowledge. And so for this, we use a process called confidence-based active learning. The key here is that when our model generates predictions, it's not just a binary yes or no, but it also gives a confidence score for each article. And so if we take the lowest confidence articles, these are presumably the most difficult and confusing articles. And if the WWF experts label these successfully and give them back to the model, then we can get very high quality data, and our model learns so much better. And this model is what we use as our final model for deployment. It's what we use to predict whether an article is relevant or not relevant to conservation or infrastructure. Now, going back to our original workflow, we see that the next feature is the keyword extractor and geolocator. Now, this is also quite intuitive. Here we see a list of around 1,000 keywords provided by WWF, and these keywords are highly related to conservation and infrastructure. We then look for matches of these keywords in our articles. Also, in this example article, we're able to match the keywords forest and tiger. Then our keyword extractor outputs these specific keywords together with their more general categories. And the main use of keyword extraction is it allows us to tag the articles, to see the relationships between these various articles, and to find patterns. The final feature I want to discuss is the event extractor. The first part of this is the named entity recognition model. This is based on a BERT model, and what it does is identify all the named entities in an article. So here in this example, we're able to identify 5 entities shown on the right, together with what type of entity it is, whether it's a person, a location, an organization. And doing this process allows us to track the progression through time, through multiple articles of certain national parks, certain companies, or any entity of interest. And all of these tools that we mentioned culminates in this event timeline. So using our previous keyword extraction and named entity recognition tool, we search for the entity Subansiri and the keyword hydroelectric. And using these, we're able to identify these 4 key articles, which tell quite a coherent story. And so if you take a look at these 4 panels, you can sort of follow the process that's going on. In the first panel, in February of 2020, we see an article about this hydroelectric plant near Subansiri River that's resuming completion after 8 years of hurdles and objections. In the second panel, which is at the end of that year, 2020, we see more plans about the construction, that it will be commissioned by March 2022. And then a few days later in panel 3, we see just more news in another news article, another news site about expediting the dam construction. And finally, in the last panel, we see in the January of the following year, the construction has started. And so really this timeline, this is the kind of insights we hope to be able to achieve with our News Panda toolbox. We hope this really shows the power of being able to identify these relevant articles, as well as identifying keywords and entities. Also later on, there will be an in-depth case study by WWF, but for now we finish up by discussing our final parts of the workflow.
Yeah, so with this project, we actually think there will be 2 parts of this final impact for this project to achieve. And the first part I'm going to talk about is this Twitter bot thing. So in addition to like having the output of the model being useful to only WWF, we think the impact could even go further to all kinds of nonprofit organizations that are working in this space, as well as the general civil society as a whole. So in this Twitter bot, we are able to tweet the output, the machine learning model output, with the relevant news information in a tweet, and then so that everyone in the world are able to see that. And then the second part is this final pilot study. We think that we will be having a joint collaboration with both the WWF teams in the US and UK, and also our field offices in India and Nepal. In this part, we're going to evaluate the model of the machine learning output, and then also elicit feedback from our WWF experts. So the pilot study is planned to take place starting from next month. And so now I'm going to hand over to our colleagues at WWF India to introduce how News Panda might fit into their current technology infrastructure and their workflow.
The last few years have seen a major shift with how data analytics can be performed, and location-enabled data has added a new dimensions to the scope. Our work here is to ensure that we are in the forefront of the chain and use geospatial data to empower understanding, insight, decision-making, and prediction. Implementing machine learning and deep learning use location data as connective thread can help automate process, improve predictive modeling, and gain a significant advantage towards our effort in conservation. We at WWF India will be using this technology to transition from a process-based modeling to data-driven analytics using the expertise of the colleague at Carnegie Mellon University with scripting and media monitoring. The data feeds into the rapid infrastructure impact analysis model RIAM within WWF, which aims to build a framework of sustainable development and help us understand how to proposed infrastructure strategy affects the quality of any connected ecosystem or critical landscape.
And yes, so essentially, the Panda, News Panda, and RIAM work in a lot of synergy because it allows us to gain value of any proposed infrastructure projects. It saves us time going through hundreds and hundreds of websites and scouting those websites and understanding where infrastructure projects are and how these proposed infrastructure projects affect our landscapes. In addition to this, what it essentially helps us doing is it helps us have faster decision support systems. These decision support system tools allow us to have greater impact in conservation. And yes, it's just not with infrastructure projects. We'll be soon using it in other areas of conservation technology as well.
Hello, everybody. I'm Mustafa from the Institute for Global Environmental Strategies, or IGS, in Japan. It is my pleasure to present the progress of an exciting project with the support of Google's AI for Social Good program. Together with Professor Patrick McSharry from Carnegie Mellon University, Dr. Sheen Jo from IGS, and Google expert Mr. Kshitij Jain, we have formed a small research group to explore the options for using AI to monitor the progress of UN Sustainable Development Goals, the SDGs, and understanding the interlinkages among these SDGs. I will first explain the background of our research, the problem we are trying to solve, how we are trying to solve the problem, how much progress we have made so far, and what we are planning to do next. Many of you are already familiar with the 2030 Agenda and the Sustainable Development Goals. It is a new development agenda by the United Nations that aims at eradicating poverty everywhere, protecting the planet, and ensuring a better life for everybody. The agenda charts out 17 SDGs, 17 individual goals that cover a broad range of issues, but all these goals are closely connected. For instance, if we focus only on economic growth, but ignore how efficiently we use our resources, we may worsen the environmental challenges we are facing and increase climate risks. So to strike a balance, to ensure the well-being of people and the planet, implementing the SDGs needs to take into consideration the reinforcing and conflicting interactions, the synergies and trade-offs among the SDGs, and plan accordingly. However, this kind of holistic integrated approach is relatively new, and there is a big gap in our knowledge on how the SDGs are interlinked. These SDG interlinkages are the focus of our study. At IGS, we started taking a look at this issue quite early, and we developed a methodology and an online tool to analyze and visualize the SDG interlinkages for 27 countries in Asia and Africa. On this slide, you can see an overview of how the SDG interlinkages tool works. It starts with identifying the causal links between the SDGs. Then we select SDG indicators with trackable data and collect time series data. We then use the data to quantify the identified causal links between the SDG targets. This is then visualized in network charts and through dashboards, and we also conduct additional network analysis for various policy-relevant issues. Here, you can see a screenshot of the interactive online tool that IGS has developed. Anybody can access and use the tool free of charge. However, in applying this methodology in more countries and at subnational levels, we have two technical challenges. First, there is a huge gap in quality indicators and data for quantifying the SDG interlinkages. Without adequate data, countries struggle to monitor and identify what actually works, implying that it is difficult for policymakers to plan accordingly. A lack of quality data for the tool has posed a challenge to its robustness in the assessment results. The second challenge comes from the lack of well-defined causations between relevant SDG targets. The SDGs cover a vast range of economic, social, and environmental issues. Limited resources is not enough to capture the full spectrum of the interactions among the SDG targets, and does not provide specific information at the technology or country-specific levels. A systematic, comprehensive approach is needed to help improve the causality analysis. Under this AI for Social Good project with Google's support, Carnegie Mellon University and IGS are collaborating to explore a combination of AI approaches and statistical techniques to help address the challenges I just discussed. The AI-based methodology we are developing involves two parts. The first one is related to imputation of missing data. And to impute missing data, we are using synthetic control methodology and random matrix theory. To identify the relationship between relevant SDGs, which is the second one, we are using AI-based natural language programming for text analysis of relevant literature. We are focusing on the impacts of climate change on SDGs, especially in South and Southeast Asia, where climate disaster risks are high and climate resilience is poor. We're expecting that the methodology can potentially contribute to monitoring the SDGs and address knowledge gaps in SDG interlinkages. We will develop two case studies in Bangladesh and in Indonesia under this project. However, the methodology will be replicable in other SDG scopes and other countries and regions. These slides provide you a visual snapshot of the methodological framework that we have developed. We will look at available data from key global databases and then use synthetic control methodology to impute missing data, which is that the top part, as you can see here, data collection and imputation. This will help us develop a complete time series database for the SDG indicators for all the countries in South and Southeast Asia. We will also identify the causal links between the SDGs through systematic literature review with AI-based natural language programming for text analysis, and also with predictive causality with the time series data that we're collecting. These two components will reinforce each other, for example, for validating the results. This helps us establish better defined causal links for relevant SDG target pairs. We will then have an improved SDG interlinkages analysis methodology which we will use to develop the two country case studies in Bangladesh and Indonesia. Here is a bit more details about the statistical methodology for data imputation. We will use linear interpolation for small temporal gaps. However, for larger gaps, we will predict missing values for a specific country by exploring data for a selected group of countries. For causality or interlinkage between two targets, we will use correlation coefficients after confirming the statistical significance through simulated surrogates based on the null hypothesis. Random matrix theory may offer a means of providing an analytical solution for establishing the significance. In this slide, you can see the NLP, the natural language programming we are applying on the collected scientific reports and academic papers. The NLP-based processing helps us match keywords through word embedding. And after we identify the top keywords, we conduct contextual mapping of these keywords, which provides the candidates for SDG linkages or the causal links. This table shows the progress we have made so far. We developed the analytical framework linking various components of the research work, and we have already collected the statistical data from major global data sources, and now we're working on the data imputation. We are collecting relevant literature, scientific literature and academic paper for text analysis and AI-based automating process and algorithm. Some literature has already been collected. And we are also developing a demo paper that we intend to present at the International Joint Conference on Artificial Intelligence. In the next steps, we will apply the methodology to develop the full set of time series database and interlinkages of climate change impacts and achieving SDGs. We will develop the relevant documentation, technical documentation as well, and deliver 2 country case studies. We will consider publishing some academic papers in scientific journals. That's all from my side. I'll stop here, but feel free to share your feedback or ask any questions. Thank you.
Hi everyone, my name is Chris Hallam. I'm the Conservation Director for WWF Lao, and I'm going to be presenting today about our project in the AI4SG program. Let me just share my screen. So in Lao, we were interested in looking at HI versus AI in a behavior change study in a protected area in southern Lao. Now, what is HI and what's AI? I'm sure everyone knows what AI is. AI is obviously artificial intelligence. It's been used in conservation for a whole lot of different things, most notably for optimization of patrol routes to try and increase encounter rates with threats, to building corridors to facilitate animal movements, analysis of wildlife images to detect individuals within photos or even species, and also prediction of conflict hotspots. HI, so human intelligence, was what we wanted to test. A lot of the drivers in conservation that are causing poaching and these sorts of things are driven by behavior, and we wanted to look at how AI could help us better identify or better design and implement behavior change campaigns. It's a lot of what we do. Traditionally, we've used a method that just uses human intelligence, but I know there's been some studies using artificial intelligence to identify individuals within networks to more effectively communicate messages on behavior change, and we wanted to explore that, but explore it in a more remote area and more organically than, say, using Facebook or apps to disseminate that information. So our HI approach was using a traditional human intelligence-led approach to designing a behavioral change messaging campaign. So identifying key individuals within communities, using focus groups, designing a messaging, and to then identify and give those individuals in the network a message that we ask them to disseminate. The AI approach is using an initial quantitative survey, small group of individuals within the community group, and using this algorithm to identify individuals based on network characteristics, such as number of connections. So we'll actually be doing this in a village, on the ground, very different to sort of an app, I guess, and using the AI to best target individuals to disseminate that information. So we've got one approach and another approach. So we basically wanted to compare the two and compare how the networks that are created with those two different approaches what characteristics do they have? Are they identifying the same individuals or similar individuals in one group and the other? And is one better than the other? Can we compare them? So given the same messaging, how do the networks compare in terms of how quickly that message is transmitted to everyone in the group, saturated, and the reach of the message, how far does it get through the community? So just thought I'd introduce our study area a bit later on. It's quite remote. So this is the Zaysap National Protected Area in southern Laos on the border of Vietnam. It's highly biological diverse, very unique area, lots of different ethnic groups in this area as well. And we chose two villages based on similar population size, distance to the reserve, access to services, all of those things, trying to match them as much as possible. So you can see some of the sort of baseline stats there, quite similar in many of those sort of variables. So our idea is to, go to these villages and use the HI and AI methods to identify networks in communities 1 and community 2, and basically compare those networks. So using some measures of network connectivity and spread, how important different aspects of that network are, and how quickly the message transmits. So following up after we establish the network with regular follow-up to assess how that message is moving through the community. So our initial timeline, which has been obviously affected quite strongly by COVID, has had to be thrown out, unfortunately. We are quite behind, but we hold pretty high hopes that we can now start implementing. So we're looking to be a little bit delayed in our implementation, but we're hoping to get out to the field during the next month and visit these villages and start seeing whether this human intelligence can beat or at least equal the artificial intelligence using this behaviours change study, a unique area in a unique area of Laos, and a really interesting case study, I think, for our program. Just to highlight some of the partners, obviously, University of Virginia, we're working with the National University of Laos Centre for Excellence in Biodiversity, Zaysap National Protected Area. I'm obviously representing WWF Laos, and we hope to engage students from the National University to help collect and learn alongside students and experts at the University of Virginia. So thank you very much, and I hope you've enjoyed the presentation.